get started with the second session of the day. Our speaker is Tristan Buckmaster from University of Leipzig. Please.
Thank you. So can you hear me? Yeah. So I guess the date is wrong. So this is joint work with Camillo Deletas from the University of Zurich and my supervisor, Laszlo Sekihidi. I'll be talking about Onsager's conjecture, which I'll bring out. So I'll be talking about the incompressible Euler equations that we've seen over the last few days. Specifically, I'll be looking at weak solutions. And one thing to keep in mind is that weak solutions to the Euler equation, there's a lot of weak solutions to the Euler equation. Some of them not physical, as was pointed out in Badash's talk. There's this paradoxical example by Schäfer and Schnirelmann, and later by Laszlo and Camillo, with regards to solutions to the viscosity, which start at rest, and then they oscillate wildly, and then they go to rest again. So I think Chitti aptly calls them nightmare solutions, because they have this sort of nightmare property. And so one thing to keep in mind with this talk is that this class of solution is very big. So lots of other people have been working on it here. Emil showed that it's particularly big. And so but why we're interested in it is that is its supposed relation to turbulent flows. So it's such a big class that we hope that we can create flows which have features of turbulent flows. The solutions that we will construct, we don't pretend that they're physical, but we hope they have as many physical properties as possible that you see in turbulent flows. In particular, for turbulent flows, you expect that the kinetic energy decreases. Of course, a smooth flow, it would be conserved in time, but thanks to Lars Onsager, he conjectured that there was a dichotomy between weak solutions which have a certain regularity, and above, so for weak solutions which belong to a Holder space with Holder exponent greater than a third, we have conservation. Conversely, he conjectured that below this exponent, below 1/3, we expect that there exist weak solutions which do not conserve energy. And so this is the subject of my talk. Now, the first part has since been completely resolved. So I guess it was first considered by a Yink. I don't know what the timeline is, the same years, but Constantine E. and Titti proved the full result. And then later Duchamp, Robert, Chetzikov, Constantine, Friedlander, Svetkoyan proved this. So this is all relating to part one in terms of conservation of energy. So I'll just mention the result of Constantine E. and Titti. So we have that if the weak solution is L, so if we take L3 in time and we have a Besov space with theta Holder regularity, theta Holder exponent or regularity exponent which is greater than a third, then we expect the weak solution to conserve energy. And in particular, this proves the first part where we consider the first part of the conjecture where we consider Holder solutions. But I wanted to outline how it was stated in Constantine E. and Titti for the later part of the talk, because we see this. You only need L3 in time. You don't need. So how the conjecture was stated before was that we look Holder in space and time, and here we're looking at, or at least, So here we're just looking at an integrability condition in time. So now I'll talk about the second part, which is that we want to show that there exist solutions which dissipate kinetic energy. So the first results which had Holder, so there was a series of results before we had Holder regularity. There was serious in L infinity, I guess. But for Holder, the first Holder result was by Delelis and Sekihide, where they proved that there exist solutions in the Holder space 1 on 10 minus epsilon, which do not conserve energy. And this was based on, what they did is they adapted many of the ideas from the Nash-Kuiper methods, and they adapted it to the Euler. So this is also convex integration, but one thing to point out is that all these new results, the techniques involved are more similar to the original papers by Nash and Kuiper on C1 embeddings. So they look slightly different than some of the newer techniques in convex integration, for example, by Svirak and Kirchheim and Müller. So this was improved by Phil Essett, and in particular, many of the new ideas that he introduced involved better transport properties of these weak solutions, and that was a big step forward in his doctoral thesis. And after that, in joint work with Delelis and Sekihide, we proved a similar result with the same regularity, but we were able to prescribe the energy profile. And why that's important is that there's been some work to consider a monotonically decreasing energy profile as an admissibility criteria, and so we wanted to construct solutions which had monotonally decreasing energy, which was not the case with Essett. So these were Essett's results were sort of nightmare solutions. Okay, and now what I want to advocate is that I don't want to advocate the original conjecture, but I want to advocate a weak version of the conjecture, which I think is more realistic than the original conjecture, and that's where it's basically the same sort of spaces that Constantine E. and Titi looked at, but where the regularity exponent is less than 1/3, whereas in Constantine E. and Titi's result, they looked at greater than 1/3. So you would have a whole spectrum of if you could prove this conjecture, you would have a whole spectrum of results.
So you call it the weak version because the time regularity is less?
Yes, so it's weaker than the original conjecture. So I don't really think it's really the weak version because I think it's the correct version, but but yeah. Yeah. Yes, it should probably be equal to 1/3.
It's not increasing nowhere.
Sorry?
The energy is not increasing, it's nowhere.
It had to have monotonally decreasing energy as well.
You said there exist solutions that do not conserve the energy. Can you add the fact that the energy is not increasing?
Yeah, so that would be a stronger thing. I have a feeling that it's not. So there's an argument about whether this will be a hard thing or not hard thing to have this monotonally decreasing energy. I get the feeling that when we look in these Bessel spaces that we would be able to construct such solutions, but that's just a guess, that we can have monotonally decreasing energy. So having So propose this new. So this is nothing. This is not. This is not something. This is in the literature as well. It's not stated where, but this is. I mean, this is also corresponds to the Kolmogorov 4/5 law, and so this is the scaling is. I mean, this sort of stuff is well known or predicted to happen. So the first result in this sort of direction, was in 2013, where I constructed solutions which have what we call Onsager critical regularity, which just means in space. So we show that there exists weak solutions. Well, I show that there exists weak solutions which for almost every time are Holder, so Holder 1/3 minus epsilon regular, which don't conserve energy. And actually, uniformly, they're only 1/5 minus epsilon. So that was the first result. And it follows from many of the techniques from the previous joint work with Delelis and Sekihide. But we have better time-localized estimates. And in fact, and I'll talk a bit about that later. And then we took this argument and we really pushed it as far as we can so far. And we managed to push this argument to get L1 in time. I should, I should note these solutions are continuous as well in space-time, but they only have an epsilon of regularity in space-time uniformly. So one of the main features of these solutions is they have incredibly complicated structure temporally, so in time. They have so the first result has a fractal structure in time, and the second result has an even more complicated fractal structure. And we need this fractal structure in order to get it to work. And that's the key idea of these two results. So they have similar estimates to the 1/5 results, but we have this extra sort of fractal structure in time which allows us to do this, to push it further. Now, all these schemes that I mentioned in the previous slides work on constructing approximate solutions to the Euler equation. So this is the convex integration. And this is more in the style as said in terms of the Nash-Kuiper C1 embeddings. So we have an Euler-Reynolds stress error, and we have a perturbation, and the idea is that each approximation we try to cancel out the Reynolds stress error from the previous iteration. And as Bartosz pointed out, these Reynolds stress errors appear naturally in the physical literature if you just consider, for example, averaged Euler. So you just average at some spatial scale a solution to Euler, then you get a natural Reynolds stress error. Okay, and so each perturbation is constructed by superimposing highly oscillating frequencies such that they cancel out the previous error. And it's very critical that they're highly oscillating. And what this means is that we can't expect that they're going to converge in some highly regular space because the derivatives are going to blow up. And the basic idea in turbulence theory, due to Richardson, I guess, at the beginning, was that you have these eddies, which at large time scales, which break up into smaller eddies and so forth until viscosity. And one important aspect is you can characterize them by the length scale of the eddy, and you also have this important turnover time. Now, the turnover time is So the time you expect that the energy is transferred from one energy from one scale to the next. Or another way of putting it is that it's the expected time that you expect large deformations of the eddies, Lagrangian deformations of the eddies. And this is the key component that comes in the actual scheme. Sorry? No, this is the original. This is the original poem. This is Swift. This is Jonathan Swift. This is the original poem by Jonathan Swift. It just happens to go with the picture. I couldn't get a picture which had the Richardson's poem, which is about eddies and going in towards viscosity. But I'm sure most of you have read this. And so I guess I don't have much time, but so the basic idea is that with this sort of idea, you can make sort of heuristic estimates where you look at the perturbation being at a certain amplitude and a certain frequency, and then you expect certain estimates based on that amplitude and frequency. And there's a scaling involved in the Reynolds stress and the perturbations, which is very natural. And these are the three main errors that occur when we're trying to estimate the Reynolds stress. So the first term is the oscillation term, and this is cancelled out with this sort of Nash-Kuiper idea, which is it's an algebraic basically technique to cancel off these low frequencies. The last error we call the Nash error, just because it has a very trivial estimate, which is very much like errors you find in Nash-type arguments. And the second error is the one where Phil Essett improved a lot, which is the transport error, which you need to control. And there's a optimization between this transport error and the oscillation error. And so it's key that you have these. These are the two top ones are the hard ones to control. And thank you for having me, and thanks for inviting me as well to the organizers.
Any questions?